direct.
Eric is right on time.
Okay. Okay, I record the session now. Hop. Bonjour à toutes et à tous. Bienvenue dans cette session du VMUG France. Alors, cette session aujourd'hui, elle va être un peu plus longue que d'habitude parce que on a la chance d'avoir 3 speakers qui vont se succéder et qui vont nous présenter un super thème sur, on va dire, de manière globale sur la partie VMware, sur l'infrastructure, ce que comment aujourd'hui et ce que demain sera comment nos infrastructures modernes. Et c'est le sujet comment de plus en plus qu'on retrouve aujourd'hui sur le terrain, sur la modernisation de l'infrastructure, du data center et tout ça. Donc, on va avoir une super session qui sera animée d'abord par Franck, ensuite Cormac et Duncan. Donc, je vais switcher en anglais puisque cette session va être en anglais. Vous en doutez bien, sauf si Cormac il peut nous faire la session en français. Il est le bienvenu parce que Cormac essaye de parler français. Il se débrouille bien d'ailleurs, donc je le félicite. Donc voilà, Franck va pouvoir faire une introduction. Frank can introduce himself in French, of course. No. So, hello, everybody. It's a great honor for hosting this session for the VMUG. Thank you again, Frank, Cormac, and Duncan for this morning. And I hope we spend a very good time together this morning. So I let you the stage, Frank. So if you wanted to start right now, it's good.
Noam. Great to be back. Hi, everybody. Bonjour. I'll start off the RoadShow, today's event. So let me share my screen. Together with Duncan and Cormac, we work in the office of the CTO of what's now called the Cloud Infrastructure Business Group. So we're responsible for the core products of VMware, the products that you typically use like vSphere, like vSAN, and maybe even VMware Cloud on AWS or on Azure or on Google. And those are the things that we focus on. My main responsibilities are resource management and machine learning. And so today I want to kick off to give you a little bit of an overview of what machine learning will bring to your infrastructure. And I can talk all day about machine learning, but I only have 30 minutes. So I need to pick only a few elements out of it. So it's a little bit of overview of these things. So I'm going to talk about machine learning today, what it will bring, what machine learning infrastructure is, how we can identify project engineering lifecycle, and how you can address the needs of your data science team, and pipelines, and how that will impact your infrastructure. And these things will actually automatically move into the areas that Cormac and Duncan will talk more in depth. So it's actually an overlap, or it's actually aligned with their sessions as well. So things that I touch on, they will dive in more deeply. So today, we actually use a lot of machine learning in our private area. So think about Uber, for example. Uber has completely displaced the taxi industry. And the funny thing is, by doing so, they created this entire ML landscape underneath their service portfolio, and that entire landscape actually fed into other companies to use their software for their own machine learning platforms. So other companies are using Uber's Michelangelo or derivatives of that into their own platforms. But we also use like Amazon and their recommender systems, or Netflix and all of that. And so that's typically what people think about when they hear machine learning. But in reality, a lot of enterprises today, older organizations, are already using machine learning or looking into machine learning to see whether they can cut cost, reduce cost, or improve revenue. And a great example is Deutsche Bahn. Deutsche Bahn is taking the logging of their locomotives to reduce maintenance costs by doing predictive maintenance. And they actually reduce costs by more than 40% by doing so. Another thing what they do is they install microphones in their busy stations, in large stations, to pick up a certain frequency for their escalators. And when they hear that frequency, they know that they have to service that particular escalator. So instead of waiting until it fails and actually impacting the passengers, they now can actually go on and take that escalator out of service in the middle of the night and do that predictive maintenance. Another thing what they do is they have on smaller stations where they don't have personnel on staff during the day, they have installed video cameras where they monitor the platforms to see whether there is debris or whether there is snow. And so if that camera detects snow or any debris, they will send out somebody to clear it up, and so the passengers can safely offload onto the platforms when it snows or when something else happens. Now, Nike is another example. A few years ago, they launched a application in America called Nike ID, where customers could actually upload photos into to Nike and use the colors into that photo to design their own sneaker. And so this was their way to allow customers directly to interface with Nike. This provided the customer to be more happy and private and customize their shoe to their liking, but it also provided the product teams of Nike to understand the actual need and the actual wishes of their customers. And by seeing this at scale, they could actually feed that into the next year release products. So the colorways for next year was actually more aligned to what they saw by what the customers were already showing them. And they also had a far more better reach by marketing, because they already had those customers' details, their emails and all that stuff. And so what happens is that the shift of selling was moved towards personal selling instead of going via shops. And so now Nike sells more than 50% directly to customers. And this helps Nike to sell more and faster to their own customers. And so what you see is that ML is just another modern way of reducing cost and increasing revenue. And that is just the main task of any CEO in any company. And so this ML it becomes this modern tool set for any company to become successful and to get that next step over their competition. And so we're not the only ones that see this. And companies like IDC, analyst companies, say this as well. They say over the next 5 years, any application will have a form of AI embedded into them. Or what we see is that companies, organizations are looking to use their own data that they have collected over many, many years and see how they can actually improve their own business processes and learn from their own data to actually cater to the needs of their customers or to improve their own business processes. And so when we talk to the CIOs of those companies, this is what we get back. This is what they want. They want us to create ML models, the element that provides that prediction or that outcome. And they say, if we're creating a model, we want it to be as accurate as possible. So we want to have a data scientist, and we want to provide them the tools and the platforms to be able to do so. And so the IT team needs to create that platform, needs to be able to create that platform as fast as possible and to cater to the needs. So self-service platforms, and provide the service and the connections to cloud services if necessary. What they also want is, of course, as fast as possible. So how fast can you give the data science team their tool set, their software, their environment? How fast can you spin up their infrastructure? These are the things that matter. Another thing is stable prediction services. Now, of course, that means the infrastructure needs to be stable, needs to be resilient, needs to be able to become available. But it also means that if a model is being deployed in production and it generates those predictions needs to be accurate all the time, even if the world changes. So think about COVID and what happened to the entertainment industry, the airline industry, the hotel industry. Every model was basically worthless. And so that's what we mean with stable prediction service, the ability to redeploy a model as fast as possible based on the changes of the world around. That means that we need to capture new data, store it in the environment, create a new data set, and retrain and redeploy as fast as possible. So typically that means there needs to be able to create a pipeline. And we need to do this on these DevOps principles, CI/CD pipelines. And so this DevOps principle needs to be ingrained and needs to be introduced into the organization. That's something that is new for some organizations. Some organizations already are adopting these DevOps principles. Now, there are some books written by Gene Kim that are very interested if you're not already aware of these principles, and I highly recommend you to read those books like Unicorn Project. This is the latest book. The last bit that I want to talk to you about is reproducibility and explainability. Once you've deployed a model, it generates predictions or a particular outcome. Now, there can be some scenarios where you need to explain to the court or to a certain government body how you came to that recommendation. Things happened in the US where somebody was convicted of something due to the fact that somebody was recognized by an AI system. You need to show that, hey, I used this model with this data set, and that caused this recommendation. And so you need to create version because you're constantly retraining, or you could be retraining. And so this versioning will mean that you need to store those models. You need to store those data sets. You need to version those data sets. So you need to create an infrastructure of stores for your data, for your models, and maybe even for your CI/CD pipelines, because they will change as well. That's a whole new infrastructure in a new environment. And those are new types of paradigms that will show up in your environment. Now, when we look at the machine learning infrastructure, we typically talk about a horizontal platform architecture with a vertical application stack. Now, what does that actually mean? Typically, when we look at the training stack, it is comprised out of many different layers. We have the infrastructure layer, and we as VMware always say, well, you need to use vSphere. But at the inference side, and inference is basically you deploy a model and it creates that recommendation, and that's typically done at the edge where actually the action happens. Now that can be in a retail organization, at a supermarket. That's an edge location. Now, you might not have room for a full ESX server. So maybe you need to have a small box. And so in some cases, Tanzu or a Kubernetes deployment is just good enough. And so we have an answer for that as well. But training, that's done with massive amounts of resources. In the majority of cases, you want to have vSphere, right? You want to have the power of a data center OS. And so you want to have parallel horsepower as well. So you want to have an accelerator that can be just a CPU in some cases, or a GPU, or an FPGA. You need to run it somewhere, so it can be a VM or a container. Well, in most cases, containers is where it's all about in machine learning. Container is the lowest level of abstraction of the data scientist. That's where the data scientist is comfortable with in operating. Not the lower levels, but that's where he or she operates in. And then we have the framework, PyTorch, TensorFlow. Those are the most popular ones, but there are plenty of others. And then we need to feed in the data. If we train, we use training data sets. Once we know that model is good enough, we will validate it with a new train, and we need with a new data set. So we need to have copious amounts of data. For the inference side, we use unseen data because that's just new data. Like if you Google or if you search something on Amazon, that's what we call unseen data. Amazon does not know what your query is. If you're looking for a toilet seat, it does not know you need a toilet seat this day, right? Those are what we call unseen data. And a model that's being deployed is what we call a converged model. Now, what I want to talk about in this session is the training, the data, and the accelerator. The runtime and the framework is in the container itself, and you need to have a way of deploying that. Now, that's something that you want to do with at the base layer of Kubernetes, and that's something Tanzu, and you want to connect it to an accelerator, and that's something that Cormac will discuss in more detail in his session. Now, one of the things that we see when we talk to data science teams and when we talk to CIOs is that they say, look, I'm a data scientist, I'm very special, and I need all the hardware that I need because my project is the most special project on earth. And so typically a GPU or data center GPU costs around 16,000 euros. What we also know is that the average GPU is utilized 4% of the time. That's really expensive. But if we look at this more scientifically, we know that making a model or developing a model, it actually follows a particular process. It follows a particular life cycle. And we can actually identify particular phases. There's this concept phase, there's this development phase, and eventually there's this production phase. And in the concept phase, the data science team is getting from the business unit, they're getting this assignment, like, I'm having this business challenge. Can you solve this with machine learning? And so what the data scientists do, they are looking at this idea, can we actually solve this with machine learning? And so they're looking at other projects. Did they solve this already? Can we solve this? What type of model do we need? What type of framework do we need? Do we need TensorFlow? Do we need PyTorch? Do we need something else? And what type of data do we have that we can work with? Where is that data in the organization? Can we reach it? Can we access it? That's the political side of things. What is the data quality of that? What is do we need to transform it? Is it in the right method? Is it in the right format? All that stuff. That takes a lot of time, right? Politics involved, getting access to it, and also the exploring of the model. They're testing it, they're trying it. So in essence, they're just running it sometimes. They're running it and they're doing bits and pieces. They're just doing it in seconds or maybe minutes. So you don't need to have that full-blown system with that 16,000 euro card sitting there. You can also run it on a CPU. So you can spin up a container with the CPU and just run it there. Or if the data scientist really wants that GPU, you can have a fraction. We have NVIDIA vGPU, and you can split it up and you can give them a part of the memory. So another data science team can have also access to that same GPU, and which maybe they are also in a concept phase for their project. We can also use BitFusion. Now, BitFusion is a server client model where we have a virtual machine with the server software. That virtual machine controls the vGPUs, and we install the client software in the container, in the virtual machine. The moment the data scientist triggers or runs a CUDA API, an NVIDIA CUDA API, basically their programming language, we intercept that, or basically the BitFusion client intercepts it, sends that code over the network to the BitFusion server. It will run the code on the GPUs and sends the results back over the network. Yeah, there is some latency involved, but we're testing here. We're doing a concept phase. So we're not latency sensitive. We're not being business revenue or critical revenue work. We're not doing that, right? Another thing what we can do is we can also do a Ryzen desktop. So this is something what we did for the Dutch Cancer Institute, which we highlighted 2 years ago at the VMware keynote, where we installed a full tool chain for the data science team for the Dutch Cancer Institute. So they have access to every bit and all the infrastructure from their own desktop, highly curated, everything what they need from any location in the world. Just log on and there you go. Now, the next step is the development phase. So they figured out what is the framework, we can solve it, and now they want to train. And so they need to have a lot of data. So they're doing back and forth, they're doing some data, we need more data, and then they train. Oh, we need more data, and then they train again, right? So this is a cyclical model. So for that, they're running small data sets and there is more time. So we still can run with fractional GPUs, with BitFusion. We can still run it from our Ryzen desktop. Now, the next step is the actual model training, because they know this is it. We know what we're going to do, but we need to have more data and we need to train it for longer periods of time. And that's what you do. But now you need to have parallel horsepower. So maybe you have a vSphere cluster with a couple of vGPUs. So an NVIDIA, a set of NVIDIA GPUs exposed by NVIDIA vGPU technology. Or you can still use BitFusion. We have customers that run model training times of 200 hours. And so with BitFusion, yeah, you have some latency, so you will add some more hours. But the fun thing is, after that 200 hours, typically the data scientists go back, look at the results, see what hyperparameters they need to tune, and then they will submit that test code again. But during that time, there is idle time. And so if you use BitFusion, somebody else, some other data science team can use that infrastructure. So this is a more economic way of doing things. And to be honest, if you're running it for 200 hours, what is 200 hours or 220 hours? But that's a discussion you need to have with your data science team, of course, and how special they are. And so the next step is, of course, actually putting it into production. Now, this is the difficult part because we need to deploy the model in production. Now, there are some tool sets out there that are making it more and more easier day by day. And so at one point, you're going to put that model in production and it's going to serve predictions. But the world changes. So what we see when we monitor the model performance, we see that the prediction, the accuracy is actually reducing. This is what we call model decay. It's decaying in the accuracy. And so maybe you need to retrain it again. So what you want to do is the data that you've been seeing feeding into the actual production environment, you want to capture that, you want to store that, and you want to have the data scientist or the data engineer to make it into a new data set to retrain a model and to push a new model back into production again. That is the continuous loop of feeding the production environment into a new model. And this is the pipeline that I was talking about, and which I will talk about a little bit later. And so we have persistent workload because we're constantly pushing a model and we're constantly feeding data into that model. Now, inference can happen in the DC. We have customers that are running inference in data center. Think about large gaming workloads. So one of the competitors of Minecraft, they are doing inference in data centers, basically text inference. And so, but we also have a lot of customers who are doing inference at the edge. Think about retail organizations who are doing self-service registers. They're doing inference at the edge because a supermarket is a edge locations. Now for that, you cannot have a massive vSphere environment. You can in some cases, but for the majority, it's a closed environment. So for that, we are looking at Project Santa Cruz, which is an SD-WAN device which just runs Tanzu Kubernetes. It has a CPU. So typically, it's not necessary to have parallel resources for some of the inference. And so that is more equipped for closed confined environments. Now I already talked about pipelines and those things. So what does it actually mean? Now this is a more complex diagram. And so in some cases, we need to ingest data somewhere. We need to ingest it from a camera system, or we need to ingest it from a particular database. And so we need to do something with the data. And from ingestion to actually moving it into a training environment, we need to do some steps. And this is a data orchestration pipeline, right? And then we train it, and then we move it from that training stack to the inference stack. So we need to have another pipeline. The moment that inference stack is actually working, we have actually two pipelines at both ends. We have incoming data into the model, and we have actually a process that will do something with that prediction or with that action. So think about controlling a robot arm, or looking at a traffic light. So, or doing something else like monitor or alarming system, right? So we're doing something when the model has decided on something. But like I said, with that model decay, if the world changes, we need to make sure that that model is accurate all the time, so we can do continuous training. Now, that doesn't mean that we're doing it in real time. It can be done on a weekly basis or on a monthly basis, but that needs to be an automated process somehow, that we capture the data and that we feed it back and that we monitor and that we log. That's something that you don't want to do on a manual basis. You can do in the beginning, but at the end, when it's more mature, you want to set this up on a more automated way. Now, this is a more complex diagram, but the idea that I want to show you is that typically when we talk about machine learning and we talk about data sets, we're talking about data sets of maybe 10 gigs or 100 gigs. And compared to a database of maybe a petabyte, that doesn't sound that, well, interesting. But the reality is that that data set is actually a very, very noisy neighbor, maybe the noisiest neighbor that you've ever seen. Because this is what happens. We want to ingest data from someplace. That can be, like I said, a video camera or something else. And so when we ingest the data, we store it in a database. Maybe that's an unstructured database. And then we need to change it. We need to transform it. So we move it from one place into another place. If we transform it, we typically do it in a Spark cluster. So that's an in-memory database, right? Maybe sometimes there's a database in front of it, right? And so we need to have some performance, some compute performance, and some storage performance, and some memory performance, right? And so Duncan's going to talk about Capitola as well that can help with this. And then you cannot use it directly into your CPU or into your GPU cluster. So you need to move it again into a data warehouse system. And so you need to have a lot of storage again, and you can have a fast data warehouse like a Redis in memory, or a Greenplum, or maybe a SQL database. And from that place, you can feed it in your cluster, in your GPU cluster. And then once you've trained it, you want to store it somewhere, you want to version it somewhere, and then you can move it into production. And so this is just a pipeline for one model. So what you see is you're going to drag a lot of data through your infrastructure, and you do this over and over again, because like I said in the beginning, with those phases, your data scientists are going to look for data over and over again. More data, more data, more data. So they're going to do versioning of data, and they're going to pull a lot of data through constantly. And if you think back to your vSphere days, think about how you set things up. Networking are just virtualized IOs. And who's responsible for those IOs? The CPU. So you're going to put a lot of strains on your CPU. So for that, we teamed up with some partners, and we created a Project Monterey, and we looked at the DPU, the data processing unit, to see whether or not we can offload the vSphere infrastructure and the IOs into a separate unit, into a separate component. And this is something that Duncan is going to talk about more in detail, to see how this unit can actually help us to get rid of that noise neighbor, or to help us process all this data for all these pipelines, for all these model developments. Now, the key takeaways that I want to leave you with is that if your company is going to look at machine learning, and if they're going to use vSphere for this, look at DevOps, see whether or not, look at CI/CD pipelines, and how you can embrace that within your vSphere environment. Think about Kubernetes as well, because the container is the lowest level of abstraction for the data science team. So create a self-service environment with a rich marketplace infrastructure, because they want to have a lot of different tools inside their container. So you want to connect with a Tanzu application catalog, formerly known as Bitnami, a NVIDIA NGC, all of that. They want to use a lot of data. So data is the first-class citizen in your infrastructure. Be prepared that this is going to be your noisy neighbor. And each phase of the life cycle requires a different platform. You don't need to provide every data scientist with their own expensive GPUs. You can do some sharing. You can make it very economical, right? The last thing what I want to say is that what we see is that a lot of customers, they start off by going to a Amazon or a Google or an Azure for their machine learning. And that makes sense, like an Amazon solution like SageMaker makes sense. But eventually, what we will see is that once they really go deep into solving their business challenges, that that system is too restrictive. And then they want to have a more open platform. And that's where vSphere shines, because you can create your own curated open platform for your data science team. And with that, I would like to thank you.
Great. Thank you, Frank. Always a good session. Very great stuff, Frank. Thank you. Cormac,
oui.
you have a big challenge to do better than Frank, and for you, especially in French. Okay?
I don't think so.
No. Okay.
I'm very much out of practice.
Okay, Cormac. Go ahead. You can start now. And if you have any question, guys, you have the chat. So feel free to ask your question in the chat. Now Frank is available, and Duncan also. So feel free for asking your question. Thank you, Frank. Again, Cormac, go ahead.
Okay, thank you. Good morning, everybody. So I am going to follow on from Frank's presentation. Frank has given us the kind of data scientist view of the infrastructure. I'm now going to move down one level and talk about essentially the layer that sits between the data scientist and the vSphere administrator, but there's sort of some overlap there as well, as you will see. Okay, so I'm going to talk about a few roadmap items. So I am including this disclaimer. I'm sure you've seen this many times before if you've seen VMworld presentations, but it's the same sort of thing. I'll talk about some things that we are contemplating. That's the best way to put it. And of course, you know, with that, these things may or may not happen or may not arrive in the time frame that we're talking about, that kind of thing. Okay, so I'm going to talk about Tanzu Kubernetes, and I think when I presented to you before, I always begin by trying to differentiate the different Tanzu Kubernetes that we have, because it can be confusing for sure. Now, we have three different flavors, essentially. There is the very first Kubernetes distribution that we released. I think we announced that at VMworld 2017, and that was a collaboration with Pivotal at the time, where we brought out the Tanzu Kubernetes grid integrated. At the time, it was called Enterprise PKS, short for Pivotal Container Service. And we had things like Bosch and a lot of those things that came from Pivotal in order to deploy out and manage your Kubernetes cluster. We then acquired a company called Heptio. I think that might have been around 2019, perhaps, something like that. And they had their own Kubernetes distribution as well. And when I say Kubernetes distribution, I just mean that they picked a whole bunch of open source packages to build out their Kubernetes distribution, and they just supported the components that made up that Kubernetes distribution. We are doing the same thing with TKG multi-cloud. TKG short for Tanzu Kubernetes Grid, by the way. This is much the same sort of focus that Heptio had, in whereas TKGM is essentially selecting a bunch of open source packages, combining them together in a stack that VMware can stand behind, can distribute, and more importantly, can support as well. The reason it's called TKG multi-cloud is it deploys on a bunch of different platforms, vSphere being one of them, but also on AWS and I think Google and Azure as well, perhaps. Now that brings us to the final TKG version. This is the TKG service, and this is a service that is part of a product called vSphere with Tanzu. vSphere with Tanzu is essentially where you install a Kubernetes control plane on top of vSphere or integrated with vSphere maybe. And from there, you can start deploying out workload Kubernetes clusters. So we use a TKG service in vSphere with Tanzu to create TKG clusters. Now, there is subtle differences between the TKG that is part of TKGM, the workload clusters that provisions, and the workload clusters that TKGS provisions. So it's a little bit complicated, confusing. Even for our documentation, it gets a little bit confusing to try and figure out, well, what Tanzu am I talking about? So fortunately, what we're doing is we understand that this is a little bit confusing for our customers to try and figure out, is TKGS or TKGM the best approach for doing Kubernetes on top of vSphere? And the great news is that we are working towards having a single unified TKG going forward. I just call this TKG 2.0. I'm pretty sure it's not going to be called TKG 2.0 because then our marketing team wouldn't have anything to work on or talk about. So I'm sure it'll come out with some wonderful fancy name to describe this unified TKG. But the point is then whether you're going to go with the this multi-cloud approach or whether you're going to go with TKGS, the end result is that the workload clusters should be exactly the same. Great. So with that out of the way, let's talk a little bit about the applications that we're currently seeing being deployed on top of Kubernetes and in the vSphere platforms today. Now, if we go back only a few years, our definition of an application was pretty straightforward and very VMware centric. So we would have had a bunch of virtual machines. Inside those virtual machines, there would be some monolithic application. And if it was a multi-tiered application, like I'm showing you here on the left-hand side, you just have the virtual machines all communicating to each other, passing information and so on. So that has changed considerably with the advent of Docker and Docker becoming mainstream. And then Kubernetes basically winning the container orchestration battle to manage and control and monitor and do all of that lifecycle management around containers. The point is that there's still virtual machines out there. There's still applications that would probably never be containerized. There are still software developers who are creating monolithic applications. So we see applications today as being a combination of containers plus virtual machines. And containers is there's a lot to be said for that sort of 12-factored app development where you build in things like replication and scale out capabilities and making them portable and so on. But there's always going to be applications that will never be refactored into this format. So as I said, we absolutely see application development going forward as being a combination of containerized apps plus monolithic applications that typically run in virtual machines. So where is the best place to run those applications that are a combination of containers and virtual machines? Well, we think vSphere is the perfect platform. And so that's why we've been so focused on doing so much with Kubernetes recently, in the fact that you can run both virtual machine workloads and containerized workloads. So I think the point we're trying to make here is that there's still going to be an opportunity for vSphere to be able to run those type of applications. And definitely vSphere administrators should be sort of positioning themselves in a way that they can manage both of these. And so with vSphere with Tanzu, that's exactly what we're building here. So what I'm showing you below the line is that, it's not for the vSphere administrator or the IT administrator just to create a vSphere platform and just hand it off to their platform operators who are taking care of Kubernetes. We think there's a role here to be played for the vSphere administrators as well. And if you look just above the vSphere platform layer there, you can see that there's a bunch of services. I've mentioned the TKG service, and I'll spend a little bit more time on that as well. But essentially, there is a role here for the vSphere administrator to still control the resources, to do lifecycle management and so on for Kubernetes platforms that are deployed on top of the vSphere platform. Now, we're showing two different roles here. We're showing the vSphere administrator role, but we're also showing the platform operator role. And the platform operator is that persona or person who is creating environments for developers, or as Frank says, also for the data scientists. Because the data scientists probably don't want to be down in, building Kubernetes clusters, building out virtual machines for what they need to achieve. They just want access to those resources. So in some cases, there may be an overlap in what the vSphere administrator is doing and what the platform administrator is doing. But I just kind of separated them out here because in very large environments, these might be two distinct roles as well. Okay, so I'm going to talk in particular about these services that are available to the vSphere administrator to control vSphere resource management when handing off resources to the platform operator who is building environments for developers or data scientists. Now, this is sort of how we see the workflow going. There's obviously somebody who's, that vSphere administrator whose core role would be managing the infrastructure, as you can see there. But there's also the transitioning of the vSphere platform to also handle Kubernetes. And so that's where vSphere with Tanzu comes in. And so again, as I said, the main role here of the IT administrator, the vSphere administrator, is just to control resources and to make sure that when there is multiple platform operators, lots of developers using the same platform, that there is a way of managing those resources. So as I said, the platform operator then could be building Kubernetes clusters, could be building virtual machines, could be building a combination of both in order to accommodate the requirements of the developers or the data scientists. And what happens then, and Frank has talked about this, is that the data scientist is building a model, but then new data comes in. They need to continuously retrain that model, and that sort of feedback can come back to the platform operator to build clusters of different sizes, clusters with different resources. Kubernetes clusters now is what I'm talking about, or VMs of different sizes, VMs of different resources, in order to be able to accommodate the new retraining of the model. So we're going to see that as well. So I've sort of broken down the responsibilities here again for the TKG service. So you, as somebody who is taking the role of the vSphere administrator here, would be responsible for things like making sure that the appropriate Kubernetes distributions are available, storage resources, virtual machine classes, which control the size of virtual machines, and namespaces, which define the overall vSphere resources that a platform operator can consume. The platform operator then will take those specifications, put them into a manifest or YAML file, and hand them off to the TKG service, which would then build a cluster that a developer can consume. Okay, so I think hopefully that's pretty straightforward, but I'm going to go through some of these capabilities shortly. Now, one thing is that you may not want to be in this situation where you're constantly having to create namespaces over and over again for different platform operators, or the same platform operator asking you for resources. So we have this new functionality now in vSphere with Tanzu, which is called the namespace service, which is what allows a platform operator to actually create their own namespaces. But you don't want them to be creating these massive namespaces and consuming all of the resources on the vSphere cluster. So again, the vSphere administrator can control the size of the namespaces that the platform operator creates. So what I'm showing you here is this is a cluster that has vSphere with Tanzu enabled. You're going to enable the namespace service so that the operators can build their own namespaces, but you can see here that you can control the resources, you can control the storage policies, you can control the virtual machine network on which that namespace has been created. And you can also add permissions. Now here, the permissions is just a vSphere.local SSO administrator, but you can imagine that if you had multiple platform operators, you could create different permissions. They would be part of the vSphere SSO. You could add in the different operators here as well. And so some operators can create large namespaces, other operators can create small namespaces. That's the idea. So with that in mind, once the platform operator is down at the kubectl, which is the Kubernetes API interface, they can actually build the namespaces. But the point, once again, is that the vSphere administrator controls the resources that the operator can consume, but also has full visibility into what they're building. So here we're looking at the namespaces in the vSphere client, and you can actually see what your platform operators are building and how much resources they're consuming and so on. So I have a short demo. I'm going to run through that now. And this is where I'm using the kubectl vSphere login to log into vSphere with Tanzu. I'm going to show the namespaces that are already available. We get a combination of system namespaces, but also workload namespaces. So here I am as a platform administrator, and I'm going to try and create a new namespace, and it doesn't let me do it. There is no capability available to do that. So I'm going to come back onto the vSphere client. I'm now the vSphere administrator. I'm going to say, okay, I'm sick of this guy constantly asking me for namespaces, so I'm just going to allow them to build namespaces themselves. So like I said before, you have control as the vSphere administrator over the resources that are available in a namespace: CPU, memory, storage policies, which control what data stores that they can provision onto. I have a vSAN here, so I'm just going to create a vSAN policy. And then the network for the objects that they create in the namespace, where do they go to? Then it's permissions. Like I said, I'm sort of simplifying it here. I'm just using the administrator SSO, but you can imagine that you could have different platform operators that you can give different privileges to. And so the point is that once these are reviewed and confirmed and the namespace service is enabled, you can now tell the platform operator who's building out environments for developers, building out environments for data scientists, go ahead, create your own namespaces. Don't be annoying me with these requests anymore, or something to that effect. But again, just to reiterate, we have full visibility as the vSphere administrator over the namespaces they're building, their permissions, the policies they're consuming, as well as the CPU and memory and storage limits and usage as well. Okay, so that's that demo. Hopefully it gives you a good idea about that particular one. And I want to talk about VM class. So we've now given a platform operator a sort of global set of resources, but we have more fine granular control as well. So remember that these platform operators are building out environments for the developers or for data scientists. One of these, well, there's two things that they're going to be able to build. The first is the Kubernetes clusters, TKG clusters. And so the size of the control plane nodes and the worker nodes are all defined by the VM class. But as we'll see shortly, they can build virtual machines as well. So again, we're in the vSphere client. Use the vSphere administrator has full control over which classes that they can have access to within the namespace. There are 16 pre-built bespoke classes available of virtual machine, but you can absolutely customize your own. And we're going to go through an example of that later on as well. So now back as the platform operator, I can now see, okay, through kubectl get virtual machine class bindings. Oh, I have these virtual machine classes available to build Kubernetes clusters or build virtual machines out of. So this now is a YAML manifest of a Tanzu Kubernetes cluster, which when applied will build a TKG cluster through the TKG service. And you can see here that one of the entries in the topology section is the VM class. And so in this case, I'm just using the guaranteed small. But the point is that your platform operator cannot build these TKG clusters with any other classes than the classes that you as the vSphere administrator has given them access to. So VM class, TKG service, we're now going to we looked at namespace service, now we look at VM service as well. So it's a similar sort of role playing that we had with the TKG cluster as well, the TKG service. So again, the vSphere administrator, full control over what classes, which OS images, what storage classes, which networks that the platform operator can work on. When the platform operator is interested in building virtual machines, they can do this through virtual machine specifications through YAML manifests using the VM service. And even better, they can do all of the guest customization that's as necessary as well. And what I mean by that is that it's using a functionality called Cloud Init, where it allows them to set up things like, there's all sorts of configuration stuff they can do, like around SSH enablement, what shell they can use, the networking configuration of the VM. It can all be built in to that configuration, put into the specification, kubectl applied to send it to the VM service, and virtual machines can be built that can be then handed off to the developers or to the data scientists, or whatever the case may be. So again, it's very much all controlled by the vSphere administrator. We've seen VM classes, namespaces already controlled by the vSphere administrator, but now we're also going to say, here is a content library that you can use, and only the OS images that are in that content library, you can use those to build your virtual machines. You can't use any other images. So with that in mind, we've seen this before. It's still virtual machine classes. So I'm back as a platform operator now, and I can see that I can use these VM virtual machine classes to build VMs. Now I'm looking at the manifest called a virtual machine manifest, and you can see that the class name goes in there as well. But there's a few other interesting things here that we did not see in the TKG manifest now, things like image name and that metadata there. So let's look at those. So once the content library has been associated with the namespace to the platform administrator, they can also query what OS images are available in that content library. At the moment, the VM service supports two different distributions. It supports CentOS, as you can see there, but also Ubuntu. So you can build virtual machines through the VM service that are CentOS and Ubuntu. And the image name just appears. This is looking at the same virtual machine manifest. And the other thing I wanted to show you as well is just in that virtual machine manifest, you can see that there's a config map reference at the very bottom. And this is where we can take the Cloud Init customization specification, if you will, and we can put in, or the platform operator can put in exactly what they need to have done to this virtual machine or guest OS when it's deployed. And all they do is they create this cloud configuration shown here on the right-hand side. They base 64 encode that. They put that into the config map, and then they reference the config map from the virtual machine manifest. I'll show you that in a demonstration shortly, but it all ties together quite nicely. You then have the platform operator kubectl applying this manifest. It's sent off to the VM service, and the virtual machine is instantiated with these details and customized with these details. So that then brings us back to what Frank was talking about earlier, is that there are, we want to enable the platform operator to be able to build infrastructure for data scientists. And one of the key components there are be able to consume GPUs or accelerator hardware. And one of the key aspects we've added to the most recent release of vSphere with Tanzu is that you can now build VM classes that have specific hardware, particularly GPUs associated with them. So let's see that. This is now just, Frank has already talked about, how we've worked with partners on creating a platform that's can be used by data scientists. NVIDIA is one of the main partners that we've worked with there. They have a whole bunch of frameworks that they're referenced at the top part of the layer. They also provide some very interesting GPUs and SmartNICs and so on. Duncan will talk about that in his session next. I'm primarily focused here on the vSphere with Tanzu section, where we've done a lot of work in order to be able to build these classes of virtual machines that can consume GPUs. So again, this is creating a VM class. I mentioned to you that there's 16 bespoke VM classes, but you can custom build your own ones. And here you can see on the left-hand side that you can also include PCI devices. If the appropriate NVIDIA drivers are installed, they will be discovered. We can select them, And again, going back to what Frank was saying, we don't need to dedicate complete physical GPUs to VMs. We can actually slice up vGPUs and associate those with virtual machines. And the point here is that we can build these VM classes that can be standalone virtual machines, but also Kubernetes worker nodes as well. So you can have Kubernetes worker nodes that are using a portion of GPUs too. Because the reason for that is that there are various ways of installing these frameworks for data scientists. Some of them can be built on virtual machine workloads, others can be built on container workloads. So you can do either or. So this is just to show you a sort of building up on what we can do with vSphere with Tanzu, TKGS, VM classes that are also consuming GPUs. So let's assume I have an environment where there's a combination of ESXi hosts. Some of them have accelerators, some of them do not. Frank also mentioned how expensive these things are. So it's quite possible that not every ESXi host in your cluster has a GPU, and it's quite possible that a lot of the workloads that you're running don't necessarily need GPUs as well, only some of them. So I'm going to deploy out my Kubernetes cluster, my TKGS cluster, combination of control plane nodes, and then the worker nodes that do all of the work. Now, these will have VM classes associated with them. So DRS in combination with vSphere with Tanzu, the VM classes and the NVIDIA drivers know where to position the worker nodes. If there is a requirement for a GPU, it'll put them on an ESXi host with a GPU. If not, it won't. So once we've done that, and once the workers are positioned appropriately, the NVIDIA has a Kubernetes operator, which includes a node discovery feature, which will figure out, hey, this worker node, this is on a, this has access to a GPU. It's sitting on an ESXi host that has a GPU installed. These workers, no, they don't. So they're able to differentiate out the two different node pools, workers that know about GPUs and workers that do not have GPUs. So now you can go and install that top level NVIDIA framework. If I mentioned these, TensorFlow, PyTorch, those are probably the most common ones. And because these workers now are identified and are labeled to say they have GPUs, the applications only get deployed on those as well. And it's all very neatly tied together. There's a whole bunch of work done between VMware and NVIDIA to make this as seamless as possible. And even when it comes to scaling out the cluster, which is something you may do, you can actually absolutely scale out, and you can request a scale out for node pool 2, which has the GPU present, and then hopefully you saw that there, it'll just position the new worker node on a host that has a GPU and can offer us a vGPU time slice. And then you can just scale out the application as well, and that will position itself on the new worker if all is going well. So that's hopefully tying all that together for you. I do have a demo. We'll run through this very quickly just to show you how this VM service works. So I'm just checking. I'm currently in that namespace that I built earlier in the previous demo, by the way. And now I'm just checking what resources I have available as a platform operator. So the vSphere administrator will have given me all of these or allocated all of these to my namespace. So I can just check these to see what VM classes. And I don't have any VM classes. So I can now request, or vSphere administrator can set this up in advance to be able to associate VM classes with this particular namespace so that I can get ahead and go and build a virtual machine. I also need OS images, so I'm going to add this content library as well. So now I should have both VM classes, which can be observed through the class binding, and I should be able to see VM images as well. And I'm just interested in doing Ubuntu this time. And 2 are returned, actually. One of them is only used, the top one is only used for TKG, but the bottom one can be used by the VM service. So the next thing I'm going to do is I'm going to fill out my user data. We saw this in the slides. So you can see this is all just cloud init. It's a there's a specification around cloud init customization and configuration, so you can just check that out. But you can see I can add a particular user to the sudo groups. I can give it a shell. I can set up my networking. In this case, it's DHCP. And then I can actually run commands. I'm just doing a very simple echo command, but you can imagine that you could actually install or pull down different software bundles or whatever as part of that run command as well. So now I can have a look at the, so now I'm going to convert that user data to base 64. So I need to encode it. And once it's encoded, I can include it in the YAML manifest. So you can see that there. There's 2 entries here in this manifest. There's one for the virtual machine, and there's one for the config map, which holds the user data. So you can see again, just the image information, the class that I'm going to use, power state. I want the virtual machine to be powered on when it's deployed, what policy, what network. The network type is vSphere distributed. We could also do this with NSXT, by the way. The VMs could be deployed onto NSXT segments. And then just a reference to the config map that has the user data that contains the encoded cloud init information. So now I can just go ahead and apply that. And this will be sent to the VM service. And the VM service should go ahead and start instantiating this virtual machine for me. And yeah, we're still waiting for some information to fill in. When the virtual machine is completely deployed, the rest of that information will appear. So you can see the deployment of the OVF templates. I mean, this isn't very exciting. It's, you know, the general run-of-the-mill sort of thing you would see. But the whole idea now is that we're enabling this platform operator to be able to build whatever developers or whatever data scientists require, whether it's clusters, Kubernetes clusters, or whether they're standalone virtual machines that they require for their infrastructure. And then we can finish this off. There we go. It looks like, I mean, I sped things up a little bit there, but last but not least, can we SSH onto it because we requested SSH to be enabled? Yes, we can. And in fact, there's the run command output as well. So all good. So I only have a few more small things to highlight for you. One of these things is about operational considerations for monitoring and logging and so on. There are a bunch of packages that can be very simply installed on both TKGM and TKGS clusters, workload clusters. In particular, if you wanted to get detailed information about what's happening at the low level inside in your Kubernetes cluster, we support Prometheus and Grafana. Now, we have developed a mechanism called the Carvel Tools mechanism. It's very like Helm charts, but we support all of this install mechanism and so on from top to bottom for your TKG clusters. Other things that might be of interest here, Contour for an ingress, external DNS, just hooks your Kubernetes cluster up to your external DNS, as the name says. Harbor, just for a secure container registry. FluentBit, that's to send your logs from your containers out to some external logging system. Could be even Loginsight. And then finally, Multus, that just allows your containers to have multi-NIC configurations if you needed them to be spanning across multiple networks. Now, as I said, Prometheus and Grafana are probably the most popular products out there. Very simple to install, and the way that the Carvel packages have been configured means that they are almost integrated with one another out of the box. So essentially, they very simple to install this, and then you can just point a browser at the endpoint, and you can see all your charts and graphs and metrics about your container. Cool. So I've been reminded that I'm talking too much. I'm just going to give one last update, and this is about backups. We don't have a wonderful story about backups when it comes to Kubernetes. I'll be the first to admit that. We did inherit the Valero product when we bought that Heptio company back a number of years ago. Few limitations. They're file level backups, which are not great. They can be a little bit slow, and it's always full backups. And there is a requirement to have some 3 bucket available to send the backups as well. But it's very simple to use, but I don't know if I would call it enterprise ready, to be honest. So we've been doing a lot of work around Velero to get it to work with snapshots. More recently, we developed a Velero plugin for vSphere. Again, I think we've made it very complex, and we put the requirements rather high on that, especially when it comes to vSphere with Tanzu, because you needed pod VMs, which in turn required NSXT, and also a data mover virtual machine. So, it's not a great story, to be perfectly honest. It is not available to all vSphere with Tanzu customers who are using, vSphere distributed networking and load balancers rather than NSXT. But the good news is that we finally have CSI snapshot support in our vSphere CSI driver. So the CSI driver version 2.5 just came out a couple of weeks ago, has snapshot support. And what that means is essentially is that the backup community, so all of our partner vendors who are in that backup space, should now be able to back up Kubernetes clusters that are using our vSphere CSI driver. Now, we haven't got that in vSphere with Tanzu yet, but it is on our roadmap, and we expect to see that appearing quite soon. And that will just mean that your backup vendor of choice should be able to back up your Kubernetes clusters, your applications, container-based applications running in those clusters, just using the vSphere CSI snapshot capability. Great. So I think I've run into Duncan's time. He's already reminded me. So I just want to thank you very much for having me at your VMUG once again, allowing me to present. And any questions, feel free to reach out to me either, in the next half hour while Duncan is talking, or you can contact me online as well. I'm more than happy to discuss any of this with you. Okay, I'm going to stop talking. Merci beaucoup.
Thank you, Cormac. Thank you. Very interesting. Duncan, are you ready?
Oui.
Duncan, the level is very high. I know that you're a challenging guy, but no pressure. But you have the last session.
Yeah, I know it's challenging, but I can do my best to one up the guys and see if I can make it a bit more French than what the others have done so far. So I will wear a nice beret. Does it look okay on me? Well, let's go back to normal.
Great, super. Duncan, this is the last session with you. Thank you again for joining this great morning with all community. Go ahead.
Oh, thanks. And thanks everyone for attending. It's great to see, such a large number of people still joining virtually and then participating in the chat as well. As Cormac and Frank also both already mentioned during their sessions, feel free to ask any questions during the session or after the session. While I'm on the slide, I'll be happy to answer any questions you have. And otherwise we can answer some of those questions at the end of the session as well. Well, Frank started talking about some of the concepts from an AI and ML perspective. And then Cormac more or less discussed the infrastructure components that are part of it. But when I talk about infrastructure components, I'm referring to the container layer that actually sits in between vSphere and of course the AI and ML workloads. So what I'm going to focus on is the bottom half of the infrastructure, so the vSphere layer and the hardware components itself, and what we as VMware are actually doing to optimize your infrastructure to run those types of workloads. Now, Cormac has already shown the disclaimer, so I don't want to spend too much time on this particular disclaimer. The one thing I do want to mention is I'll be discussing two particular projects, Project Capitola and Project Monterey. These projects are still under development. They may or may not be released as a product over time. So take that into consideration when you listen to some of the things that I'm presenting. Now, Frank showed you some of the use cases that customers and partners have for AI and ML. And I think this is probably one of the most interesting things that is happening today, the way that people are transforming the business by simply looking at data and analyzing the data. Now, that sounds very easy, and it's not easy at all. It's actually very challenging for customers. And what we've seen over the last couple of years, that when it comes to transforming your data based on the business, a lot of these projects that are instantiated actually end up failing. And it's a significant number. 47% of all AI and ML projects do not go from pilot to production. Now, this is based on data that was provided by Gartner. The reference is at the bottom. But I think, it's an interesting number. You may ask yourself, why is this number so extremely high? Well, there are a couple of reasons why this number is relatively high. First and foremost, when you start deploying these types of solutions, and you've seen Frank talking about it, and you looked at all of the different components, there's a lot of different pieces that need to fall together before you actually have an end-to-end solution that potentially can provide you useful information or derive useful information from that data that you're presenting to the system. And I'm saying potentially because whenever you start mining for something, you never know what you're going to hit, right? It's the same when you're mining, for instance, for crypto, or when you're mining for even physical gold, you don't know if you're going to hit something. And the same applies to data. Now, the second problem that customers typically have is that there's a performance aspect to this as well, right? When you run these analysis, when you run your AI and ML processes, of course, you want to receive the outcome of that analysis within a reasonable amount of time. That could be 15 minutes. That could also be 5 days or half a year, depending, of course, on what data set you are analyzing and what kind of outcome you're expecting and what you want to do with that outcome. So performance is also an aspect that comes into play. And then last but not least, of course, there's the operational aspect and the scaling of the solution itself. So how do you deploy these GPU resources? How do you deploy DPU resources, so smart NIC technology? Do you have sufficient memory? Do you have sufficient CPU? And how do you manage all of these systems? So which tools are you using to manage the solution end to end? And those things are now what are causing, well, probably, I'm not sure if I should use the word problems, but there are actually challenges for customers in terms of the adoption of AI and ML workloads or solutions in their environment. Now, there is, of course, a solution that can help you with the deployment of these types of workloads and with the adoption of these types of workloads. And Cormac has already alluded to it, and that's NVIDIA and VMware's AI-ready platform. And the great thing about this solution, in my opinion, is that it comes with both the NVIDIA AI Enterprise Suite, as well as it's fully supported and can come with VMware vSphere and Tanzu. So that makes the deployment of the applications of all of the different processes on top of that platform extremely easy. The other thing which is also, I think, very interesting is that, of course, we've selected servers, NVIDIA and VMware, that are supported end-to-end to run this platform as well. And this is something that a lot of people tend to skip over, right? You just need a bunch of servers, you may need some GPUs, you may need a couple of, fast NICs and maybe some switches, and there you go, you have things up and running. But reality is that when it comes to AI and ML workloads, you want to make sure that what you are running not only is the hardware layer is optimized for that solution itself, but of course also supported by both companies, NVIDIA as well as VMware in this particular case. Because when you start hitting particular challenges, we will need to be able to actually reach back to that company and try to figure out what is happening. So that's where the AI-ready platform comes into play. Now, the hardware aspect is an interesting one, and this is very similar to what we've done in the past with VMware vSAN. With VMware vSAN, we have these ready node configurations, and that's basically what NVIDIA and VMware did to figure out if we can create these optimized solutions from an AI and ML perspective for customers. So in this particular case, of course, there's a long list of different types of servers, and you may ask yourself, why would I need to have a particular type of server? Can't I just use any server? Well, if you've used GPUs in some shape or form before, you know that they can require a significant amount of power. That's why these servers need to be configured specifically to be able to run GPUs. Then last but not least, of course, the other thing that I need to mention is the networking aspect. And that is also something that is part of these configured, pre-certified configurations, the network aspect, the smart NIC. And there's a key reason for it, of course, right? Frank has already mentioned it in his part of this roadshow. When you start analyzing data, one of the key things that typically happens during the process is data movement. And data movement can take a significant amount of time, especially when your environment is not optimized for it. And that is where a smart NIC comes into play, because this actually optimizes the data movement from source to destination. And that source and destination, of course, could be a data lake of some form, or maybe another type of database, of course, depending on what you're doing at that particular point in time. But that's why VMware and NVIDIA decided to create this stack that optimizes the deployment of these applications at this particular point in time. And I'm saying at this particular point in time because the NVIDIA AI Enterprise Suite is actually available today. So you can start deploying these workloads right now. If you buy these types of configurations, you can select the GPU that you need, you can select the DPU that you need, and of course the server model as well, and start running these workloads with the NVIDIA software that is part of that solution, and of course the VMware stack on top of that. Now, when you start deploying these types of solutions, one of the things that always arises is, the question around performance. And Frank already alluded to it. He said, the data scientist always asks for more resources. And I think they're very similar to what developers used to do in the past, or application owners, right? They always wanted to have the largest virtual machine. They needed to have a virtual machine with 24 vCPUs, and 5 terabytes worth of memory, et cetera, et cetera. And the data scientists are starting to do the same thing. They're requesting physical machines, they're requesting insane amounts of memory, et cetera, et cetera. And when you start talking about virtualizing these workloads, they will tell you, well, you can't virtualize it. There's an insane overhead, and it's not going to be able to run efficiently. But if you look at these numbers, or if you look at this particular graph, it actually shows you the green part is virtualized, the gray part is bare metal, that the overhead is actually in the single digits. So we're talking about a relatively low amount of overhead when you start virtualizing these workloads. Now, as Cormac mentioned, the big benefit, of course, of virtualizing these workloads is that you get a virtual GPU, that you can benefit from things like DRS, so initial placement. And then, of course, if some type of maintenance needs to happen during the day, you could potentially also leverage something like maintenance mode to move workloads from one host to the other. Now, one thing I do want to point out, because I have some customers that actually try to do live migrations during the day while the environment was actively being used, is that when you move a workload that has a vGPU assigned to it, that there could be some downtime associated with it. And maybe downtime is not the right word, but the stun times for the virtual machines when they are actually being moved could easily be 20 seconds, depending on the amount of data that needs to be moved from the source GPU to the destination GPU. Because, of course, the data that is being analyzed, that's actively being used by the GPU, also needs to be moved around. So that is something to take into consideration when it comes to DRS. So automatic migration between hosts may not be the smartest idea, but DRS initial placement could be very useful to ensure that you have a well-balanced environment. Now, of course, besides being able to do smart things today, we're also working towards what potentially you could do with your environment in the future. Now, there are two main projects that we are working on. First of all, Project Monterey. Frank has already mentioned it briefly. Project Monterey is our project around smart NIC technology, or DPU technology, data processing units. And the thing with Project Monterey is what we're aiming for to do is to make the adoption of smart NIC technology in the enterprise a lot easier, and hopefully be able to provide you with a solution that will enable end-to-end management in a very efficient way. Now, when you look at Project Monterey, I think the key thing to understand about these types of solutions is that basically with a DPU or a smart NIC, you end up running a server within a server. So basically you have processing power on that NIC, on that network interface card. You have memory on that network interface card. And basically we allow you to start running a workload on that network interface card as well. So it's literally a server within a server. There is a couple of benefits, of course, when it comes to adopting this model, and it's all around the performance aspect and of course the security aspect as well, because we're introducing a server within a server, and you're able to actually start offloading some parts of the hypervisor to that smart NIC. We now introduce a barrier as well when it comes to security. So we're introducing an additional layer on which you can actually start running things like networking services, infrastructure management, or storage service even. Now, I've already mentioned networking and storage, and of course, these are part of our main use cases when it comes to the adoption of smart NIC technology. Now, of course, we're not just talking about routing, we're also talking about, for instance, security. You can imagine that, for instance, you'll be able to move NSXT from the hypervisor itself down to the to the smart NIC and actually do all of the firewall capabilities, for instance, on the smart NIC instead of having the hypervisor handling that. And there are a couple of benefits around that. For instance, the x86 cycles, so the gigahertzes that you normally would be consumed by the hypervisor or any virtual appliance that has to do with NSX, would now not be consumed on the hypervisor, but it would actually be consumed on the NIC. So those gigahertzes are now freed up for other workloads that could potentially be deployed in your environment. Same applies to a storage perspective, right? We have vSAN running within the hypervisor. You can imagine that when you have sufficient CPU power on the smart NIC available and sufficient memory available, you can now actually start running those services, the storage services, directly on the smart NIC, so on the DPU, which not only will allow you to offload vSAN to the DPU itself and free up those resources, but potentially may also allow you, for instance, to expose vSAN directly to, for instance, a bare metal solution. So you could have Windows running on a server, which then consumes vSAN through the smart NIC directly, because the smart NIC is running vSAN, or potentially, Windows running directly on bare metal and have a smart NIC running with NSX. So that is something that we are exploring for Project Monterey. Now, if you look at these devices, what do they actually look like? Well, if you look at this device in particular, it actually looks like a regular NIC, right? It just looks like a regular network interface card. However, the big difference between these types of solutions, between a regular NIC and a data processing unit or a smart NIC, is the processing power that is available on that smart NIC, the memory that is available, and the fact that there's a programmable aspect as well. And you can start running software directly on that NIC. So the other thing, of course, that I should point out is, and I think that is also something that is interesting when it comes to these devices, that these devices will typically come with a management interface. So that's why I'm saying it's almost like you're running a server within a server. On top of that, because we have that programmable aspect, you can also now start virtualizing or creating virtual devices and actually expose those devices across the network. And that could be, for instance, things like an NVMe device. So you're running vSAN, you've created an object or a LUN on top of vSAN, and that LUN on vSAN is now exposed as an NVMe device to another physical host, which could be part of a vSphere server or could potentially be running something like Windows or Linux. All of those different abilities will be made possible through the DPU or the smart NIC technology. Now, there are a couple of vendors that we're working closely with to start introducing this solution into the data center. Of course, NVIDIA is one of them. NVIDIA acquired Mellanox not too long ago, and through Mellanox, they're actually releasing this smart NIC technology to the market. There are two other main players that we are working with. Of course, Intel. Intel is probably one of the largest manufacturers when it comes to CPUs, but of course they also do network interface cards. And then last but not least, Pensando. For those who don't know Pensando is a startup, so they haven't been around for that long, well, not at least when you compare it to NVIDIA and Intel, but they are doing extremely well in the smart NIC space. So those are the three players that we are working with from a design perspective to design Project Monterey. Of course, we're also closely working with the server vendors, because the server vendors also need to be ready for this. They may need to start making changes to their firmware. And of course, they need to be able to sell these platforms as well. So we're working closely with Dell Technologies, for instance, HP and Lenovo, to ensure that what we are building not only meets your requirements, but also meets their requirements. Now, I've already briefly mentioned this. If you look at NSX today, NSX today runs on top of the hypervisor, and that actually means that it consumes the resources of the hypervisor as well. In most of the cases, when customers start looking at the solution like NSX, what they will end up doing is they'll typically implement, a fast networking layer as well. That could be 10 gig, 25 gig, or even higher. But of course, what we are working towards is actually delivering these solutions on top of the smart NIC technology by virtualizing those smart NICs. In the future, we will be able to actually start running those workloads directly on top of the smart NIC. So not only freeing up the x86 resources for other virtual machines or containers or whatever it ends up being, but also have a more efficient platforms in terms of how we handle network traffic and do things like firewall. And I think the great thing here is that the networking aspect and the security aspect actually happens on the layer where it should be happening, which is the NIC itself. So if traffic needs to be blocked, it's not going to be blocked by the hypervisor, but it's going to be blocked by the NIC. So it doesn't need to be handled by the hypervisor even at that particular point in time. And I think that is probably one of the biggest benefits of this solution overall. Now, you may ask yourself, okay, that sounds great, but what does that actually result into? And of course, we did a couple of tests with NVIDIA to figure out, what that actually looks like when you start virtualizing these devices and you start running things like next generation firewalls on top of a smart NIC. And I think the interesting thing here is that if you look at the three graphs, is that there's a big benefit from a CPU perspective, so the consumption, from an instance cores perspective, but also the amount of bandwidth that a solution like this is capable of driving when it actually leverages the DPU. Now, I think the nicest one is the graph in the middle. If you look at the graph in the middle, it actually shows you that when we would run a firewall like this on top of the hypervisor, 12 cores would be consumed fully. When you run it on top of the DPU, of course, no cores would be consumed. So that is the biggest benefit that you will have here, because those cores are now available for other types of workloads to start running. And on top of that, not only can you run other types of workloads, these workloads will also run more efficiently because they don't need to be scheduled next to, an appliance which is consuming an insane amount of CPU cycles. So ready time and those things will go down. Now, that is the networking aspect of things. The other thing that we've also heard during the sessions, and Frank already mentioned this, is the memory aspect of it. And I think the biggest challenge that customers have when it comes to memory resources is that they typically don't have enough. When we talk to customers, and this has been the case for the past 20 years, one of the things that they always challenge with is the amount of memory capacity that they have available. And there are a couple of, challenges that are now starting to pop up on top of that, because more and more customers are deploying these larger memory intensive workloads. The cost of their environment is also going up. So what they are asking us is, how can we reduce the cost of the environment while still providing a higher amount of memory capacity to our customers? Some customers are deploying extremely large databases, for instance, and those databases start, in some cases are even doubling every 18 to 24 months. So you can imagine what kind of pressure that actually puts on the infrastructure layer. And of course, for customers who run, something like a service provider, so some of our VCPP partners, one of the things that they are most interested in is actually lowering the overall cost of the environment. Now, we're starting to see different types of solutions, of course, emerging in the markets, things like persistent memory. Could that potentially be used to reduce the total cost of ownership? Well, those are things that we are now exploring, of course, with Project Capitola. There are a couple of other challenges that we are facing, and I'm pretty sure that some of you may have hit these problems at some point in time, but you may not have realized, what some of the reasons are behind it. If you look at memory, and those who haven't seen the session by Frank Denneman at VMware about NUMA, I would highly recommend watching that one, because it goes into an extreme amount of depth when it comes to memory configurations. But one of the challenges that customers have when they start configuring their service, when they start speccing their service, is figuring out how many DIMMs do I need to have to run an optimal configuration, and what is the maximum number of DIMMs that I can have within that particular server, and what is the maximum amount of memory that I can have in this particular configuration. It's a very challenging problem, especially if you look at the amount or at the capacity of those solutions as well, right? Over the last couple of years, 32 gigs, 64 gig DIMMs are starting to become more popular. But if you look at the price, it's still relatively expensive. And, that typically poses a lot of challenges. Of course, you could start off with, let's say, 16 gig DIMMs and then over time start upgrading it. But when you upgrade a server, you actually need to go to the host itself, physically remove the DIMMs that you have in there right now and insert new DIMMs. And that process itself not only is costly, it's also challenging, because in a lot of cases, our customers can't just walk into the data center to start ripping out stuff and replacing it. So with all of these different problems combined, what we wanted to do is we would want to start looking into how we could solve these problems. Now, we're not only looking into solving these problems, of course, the industry is also looking into how they can solve this problem. And one of the ways the industry is looking to solve this problem is by introducing a new protocol. And this protocol is called CXL, which stands for Compute Express Link. And CXL is actually a protocol that runs on top of PCIe. And basically what it allows you to do is it allows you to provide memory resources to the CPU over a PCIe bus. You could probably say that it's fairly similar to persistent memory, but persistent memory actually sits within a DRAM slot. In this particular case, you potentially have DRAM actually exposed through PCIe using the CXL protocol. Now you may ask, what does that look like? And it actually looks like an SSD, a flash device, but in this particular case, it's actually a memory expander that is being developed by Samsung. And of course, there are multiple different vendors working on these solutions. The interesting part of this, of course, is that you will have additional memory resources that are provided through a different mechanism. So you're not limited to the number of DIMM slots you have available. And it may also introduce some challenges because the latency is going to be different. So the latency from a memory perspective typically is in the low nanosecond range. This may be slightly higher. So we may be talking about hundreds of nanoseconds, who knows, right? But that may pose some challenges. So we as VMware are looking to solve those problems, not only to make memory management more efficient, but also hopefully to lower the total cost of ownership of your environment. So how are we planning on doing this? Well, it's fairly straightforward. One of the first things that we are exploring is how we can actually start exposing different types of memory to a virtual machine as if it's a single type of memory. So as you can see on the right side, in this particular example, we have two different tiers of memory, both DRAM as well as a cheaper type of memory could, for instance, be persistent memory. But when it's exposed to the virtual machine, it's actually exposed as a single layer. So that virtual machine just sees one big block of memory. So it potentially sees 8 gigs of memory or 16 gigs of memory, depending on how much you have exposed. And then, of course, the hypervisor is going to determine, based on certain metrics, where the data or where the memory blocks or memory pages, I should say, are going to be stored. So that is the first thing that we are now exploring. How can we actually expose different types of memory within the same host to a virtual machine as if it's a single layer? Now, of course, the question then comes, okay, if you can do that within a single host, will you also be able to do that across multiple hosts? And this is also something that we are exploring. The first thing that I do want to mention here is that, of course, when we're talking about latency and you go across a network or potentially a CXL bus, that the latency is going to be increased. So the speed from a performance perspective, of course, will change when it comes to accessing those memory pages. However, when we start talking about memory pooling, it does open up a lot of different use cases, a lot of interesting use cases, because if you have, let's say, 5 hosts within a cluster and one of your hosts is running out of resources, or you need to have, let's say, 384 gigs exposed to a virtual machine, but not a single host has 384 gigs available within that host, you can now start pooling these resources and actually expose them to a virtual machine as if that virtual machine has all of those memory resources locally. Yes, accessing some of those pages, depending on where they are stored, may be slower, but at least you have the ability to create these virtual machines that have a lot more memory available. So, you know, it's a very interesting solution if you ask me. Now, of course, you may ask yourself, how does that actually work? What does that actually look like from a hypervisor perspective? And I think it's an interesting one, because when you randomly start placing data on random locations, memory pages on random locations, the performance could be significantly impacted. But of course, we wouldn't be VMware if we would have a smart mechanism around this. And you could actually see this as the DRS for memory management. So what we're going to do is we're going to track all of the different memory metrics, and based on the access pattern of the memory page, the VM monitor is going to determine where the page is going to be stored. That could, of course, be within the host. So there could be multiple tiers within the host, or that could be across hosts as well, if that is something that is available within your environment. And then, of course, we're also going to feed that information into DRS. So if at one point in time, a particular host doesn't have sufficient memory pages available, or doesn't have sufficient memory capacity available in the tier that you would require for your workload, then DRS will also be able to pick up that virtual machine and move it to a host that does have the memory capacity available in the correct tier that your workload requires. So that is something that we are working towards right now. Smart memory placement based on the access pattern of the memory itself. Now, that all sounds great, but from a performance perspective, what does that actually look like? And of course, we've tested this. Now, I want to point out that these are very preliminary tests. So it's at very early stages, but I do think it's interesting to show you what the potential impact could be when you run multiple different tiers of memory. So the first part, what I want to show you is the situation where there is no intelligent tiering enabled at all. If you look at the 1.0, which is the normalized throughput, this is a situation where we actually have 32 gigs of DRAM. So 32 gigs of pure DRAM. So that in a normalized fashion is the baseline. So that's 1.0. When you go to the next step, which is 16 and 16, which is 16 gigs worth of DRAM and 16 gigs worth of persistent memory, you can see that there's an immediate performance drop of 23%. And when you start shifting that ratio, you go from 8 gigs of DRAM with 24 gigs of PRAM, or all the way down even to 2 gigs of DRAM and 30 gigs of PMAM, you can see that the performance starts degrading extremely fast. But this is without VMware actually interfering. This is without VMware actually placing that data, placing those memory pages on the tier that actually belongs to. And when we actually start interfering, when the hypervisor actually gets involved, this is where it starts becoming interesting. Because now all of a sudden, when you look at the 16-16 situation, where we have 50% of our memory pages within DRAM and 50% in PMAM, when VMware gets involved, when the hypervisor actually monitors the system and places the memory pages where it feels it should reside, the performance drop isn't 23%, but all of a sudden it's only 6%. And when you shift it down to 8 gigs worth of DRAM and 24 gigs worth of DRAM, it's only a 7% performance drop. So the performance drop is relatively low, even though you're using a relatively low amount of DRAM and a significant amount of PMAM. Of course, it will depend and will differ per workload, but I do think it's an interesting, it actually shows you what the benefit could be of this solution, how it could bring down the TCO of your environment with a minimal performance impact, especially in those environments where you're not constantly accessing all memory pages all the time. And I would say that's probably a large number of environments out there. Now, hopefully over the past 30 minutes or so, in my particular case, and of course the sessions of both Cormac and Frank as well, we've been able to show you not only what AI and ML looks like from a process perspective in Frank's session, what our Tanzu portfolio can bring to you when it comes to adopting these workloads. But of course, on top of that, also what we are working on from a roadmap perspective to ensure that you can start running these larger data sets on top of your infrastructure, analyze these data sets in a more efficient way, and actually also start moving the data around between those systems whenever it's required. The last thing I want to point out, First of all, of course, thanks everyone for attending. It's great to see such a large number of people. But the other thing that I want to point out is that Frank Denneman, Johan van Amersfoort, and myself recently started a podcast. The podcast, of course, is in English, and it's available for free on various platforms. So make sure to subscribe if you haven't done so yet. If there are any questions, happy to take any additional questions. I noticed the questions about the CXL protocol. I'll tweet out a link to a couple of documents that I've seen around that. There are a couple of interesting documents and papers on the CXL protocol. And it's pretty deep information, but it's an interesting solution that will pop in the near future. So I'll make sure to tweet that out.
Okay, thank you, Duncan. Please, the community, if you have any question, it's your time. So you can switch on your microphone and your camera if you want. We have time to have a discussion with our speaker. So don't be shy. No question. Allez, come on. First question.
Or do we get Hellfest tickets?
It's very difficult this year.
I can imagine.
Just for your information, we host for the first time Metallica. So it's a big announce this year.
Thomas is saying that he needs to digest all of this. And yeah, I can see why. It's a lot of information in an hour and a half or 2 hours. If anyone, of course, has any questions after the event, right, we're all on Twitter. All of us are also on LinkedIn. So, feel free to connect on LinkedIn and send a message on LinkedIn or send a message on Twitter. And I'm happy to answer any questions you have afterwards on those platforms as well. That, doesn't matter.
It was just a question about I'm discovering for this new kind of NIC, and there was something that we have when you do filtering with DVS. There is a DVS filter, so you do it from the software point of view. This is one of the way that you can do firewalling. If you do the firewalling then to the NIC, is there something that is there something really interesting? It is the same thing, different thing?
Yeah, I mean, it would more or less be the same thing, right? So if you look at these different smart NIC technologies, and I don't know if people have seen the demos that were presented at VMware 2 years ago, but the amount of processing power that these new smart NIC technologies provide actually allow us to run a hypervisor on top of the platform itself. So we could potentially run ESXi on top of that platform and run those filters on top of ESXi on that platform itself instead of on the x86 platform. So there are a couple of ways that we can go about doing this, but yeah, it's interesting, and we can definitely move all of those, different networking solutions down to the smart NIC technology, but also the storage solutions.
Okay, thank you.
Guys, I have a question. Hi.
Hi, Eric.
Nice to see you. My question is related to the RAM memory problem. It's just you have more and more features and protocols. I know about protocols. You need some hardware, but did you plan something for us? We have a small home lab at home. Did you plan something for us to be able to learn about some your integrated products and so on? Because it's becoming more and more difficult to catch up with all these innovations, and we all have home labs, not data centers at home.
You don't have a data center at home?
No, sorry.
That's surprising. Actually, I was tweeting about that not too long ago in Germany. Just the name slips me, but there's a person who invested 180,000 euro into his home data center.
Yeah.
So, yeah, no, it's I know it's nuts, but yeah, I mean, one of the things, of course, depending on how many hosts you have, you could imagine that the pooling of memory is something that would be possible at a home lab if you have 2 hosts or more. That is definitely something that we would be exposing. The other thing that I could ask the team if that is something that they would be willing to explore is that you could start testing this with potentially virtualized devices. And the way I probably should explain this is that if you look at the way that VMware tests their software, of course, we test our software on top of physical systems, but we also have a very large development cloud. And in a lot of cases, we actually mimic persistent memory, or we mimic different types of memory devices and expose those to a virtual hypervisor as if it's a physical device. So that allows us to test these different types of solutions. I'm not sure if that is something that they will expose to home labs, or will provide as a mechanism to home labs, but I can definitely ask. I mean, in the past we've seen partners, and it's a long time ago. I know Frank, when he worked at Pernix was actually working on a memory driver for the longest time to do something similar, right? So we have those solutions available. It's just that it's not, available for the general public just yet. But yeah, I think it's a fair comment.
Yeah. Okay, so that's nice. So keep us informed if you can.
Sure, I will.
Thanks.
And it was actually Mark Huppert who invested 180,000 euros into his home lab. So
think about the presents he needed to buy his wife in order to get this one through.
Yeah.
Think about the noise of the fans and the bill for the electricity.
Yeah.